This thing is huge. It's a 27 kilometers underground ring located at a CERN facility near Geneva, Switzerland. What if the universe you see is only the front cover of a much bigger book? On March 12, 2024, at 3:47 a.m., deep under the France-Switzerland border, a CERN team powered up a quantum simulation to model reality at its limits. The goal was simple: recreate conditions from the first microseconds after the Big Bang and watch the rules emerge. Instead, the output broke the script. It didn't resemble error or random noise. It resembled a structure. A repeating, self-organizing pattern appeared, held its shape, and returned again every time they ran it. They gave it a name: the Lattice, CERN, and the hunt for the universe's rules. Most people hear CERN and picture the Large Hadron Collider, a 27 kilometers ring where protons race close to light speed before slamming together. For decades, those collisions have acted like a cosmic flashlight. They helped confirm the Higgs boson, test ideas about antimatter, and recreate tiny echoes of the early universe. But there's a limit to brute force. You can smash particles harder and harder and still miss the deeper pattern if it hides in how space and fields organize. That is why CERN's quantum technology teams began leaning on a different tool: quantum simulation. Instead of building a bigger collider, they try to build a controllable quantum system that behaves like the system they want to study. It's like making a model airplane, except the model doesn't just look right. It follows the same equations as the real thing. In early 2024, the target was extreme conditions similar to the first microseconds after the Big Bang, when energy densities were so high that the familiar behavior of matter may have been only a temporary phase. The point wasn't to discover a new particle in the usual sense. The point was to watch the rules themselves under stress and see if anything unexpected appeared. The night the simulation stopped obeying expectations. According to an internal memo later circulated among collaborators, the anomaly showed up on March 12th at 3:47 a.m. Central European Time. Dr. Amara Okonkwo, who led the theory side of the project, first assumed something boring: a timing glitch, a calibration slip, a stray bit of noise creeping into the readout. That's the usual story in a lab. You see something weird, you blame the machine, and you move on. But the team didn't move on. They reran the exact sequence. The same signature returned with the same geometry, the same rhythm, the same eerie consistency. Then they altered the inputs. The pattern shifted only when the simulated energy density crossed a specific threshold, and only in a specific region of the virtual spacetime. Below that threshold, the system behaved like the textbooks. Above it, a new order emerged. It wasn't random. It looked like a self-organizing structure repeating and stabilizing itself as if it had an internal logic. In their notes, the team started using a shorthand name so they could talk about it without constantly describing it. They called it the Lattice because it resembled a hidden scaffolding of nodes and links, forming beneath the familiar quantum fields. What the Lattice looked like, and why it scared them. To understand why the Lattice mattered, imagine space-time as a flexible sheet. In Einstein's picture, mass and energy bend that sheet, and gravity is the curve. Now, imagine that under the sheet, there is a frame, a deeper support you never knew was there. In the simulation, the Lattice appeared right when the energy density spiked into a regime that resembles the universe's inflationary era. That violent burst of expansion just after the Big Bang. Instead of fields fluctuating messily, they snapped into patterns, nodes, connections, music pathways. Almost like a circuit diagram drawn by nature. Dr. Mickey Solve compared it to ice crystals on glass. Water molecules move chaotically until a temperature change suddenly makes order bloom. But here, it wasn't water turning into ice. It was the simulated spacetime itself becoming structured. The unsettling part came next. When the simulated energy dropped back to normal, the Lattice did not dissolve. It stayed embedded like a scar, as if spacetime remembered the phase it had passed through. And inside that scar, the nodes did something that looked like communication. Quantum states shifted across distances in a way that resembled entanglement, but broader, more worked, almost infrastructural. It was as if the lattice wasn't just a pattern. It was a substrate, a hidden layer, where information could move along routes our usual models don't include. A hidden layer of reality, not a new place. Nobody at CERN claimed they had opened a portal to a parallel universe. That's not what a simulation does. What it can do, though, is expose what the math predicts should happen when known physics is pushed into corners we can't reach directly. The lattice looked like a stable structure underlying the quantum world, and that idea lands in familiar territory. String theory has long suggested extra dimensions curled up so tightly we can't see them. Quantum mechanics already tells us particles can exist in superposition, holding multiple states at once until measurement forces a choice. The lattice goes one step further. In the models built around the anomaly, spacetime itself behaves like it can enter phases the way matter can. And those phases can leave behind persistent architecture. Dr. Elena Vasquez, cosmologist asked to review early drafts, framed it with a chilling question. If a stable structure sits beneath our visible reality, what kinds of patterns could form there? Not life with cells and blood, but organized information that evolves under rules we haven't mapped. Some researchers began using the phrase subquantum realm, meaning a layer below ordinary quantum fields, where the ingredients of particles, forces, perhaps even time's flow might be assembled. If that idea holds, then what we call reality is not the foundation. It is the surface expression like ripples on a deeper ocean we've never had instruments to touch. Why? It could explain dark matter entanglement and even the mind. Speculation can run wild here. So the careful approach is to ask if the lattice were real. What puzzles could it make less mysterious? Start with dark matter. Astronomers see galaxies spinning as if extra mass is holding them together. Yet that mass emits no light and barely interacts with ordinary matter. If the lattice is a hidden structure in spacetime, dark matter might be a gravitational shadow of that structure. Not a new particle, but an unseen architecture tugging on the visible universe. Next is quantum entanglement, the spooky action that bothered Einstein. Two particles share a state so tightly that measuring one seems to affect the other instantly, even when they are far apart. If a lattice-like network sits beneath spacetime, entanglement could be less like magic and more like a shortcut. A hidden pathway connecting points that look distant only on the surface. Then comes the most delicate idea, consciousness. There is no solid consensus that the mind requires quantum effects, and many snorts physicists reject the leap outright. Still, Dr. Yuki Tanaka, who studies possible links between neural activity and quantum behavior, has offered a cautious thought experiment. We know awareness correlates with brain signals, but correlation is not the same as cause. If hidden layers influence how information organizes at tiny scales, it is at least worth asking whether that influence could shape how complex systems like brains stabilize patterns. It's provocative, but it's also how science moves forward by asking questions that sound impossible until they don't. The hard part now, proving it's not just beautiful math. Every responsible scientist involved has repeated the same warning. A simulation is not proof. It is a prediction engine. Dr. Okonkwo has said the lattice might be a feature of the equations. It's not a feature of nature, and only experiments can decide. So the next phase is verification. Other groups must reproduce the result using different quantum platforms and different error models. At the snort's same time, teams are combing through real-world data for hints of an underlying texture. LIGO researchers are rechecking gravitational wave events from black hole merges for tiny fluctuations that don't fit standard templates. James Webb observations are being compared against early universe models to see whether the oldest light suggests spacetime began perfectly smooth or subtly granular. Particle physicists are revisiting decay records, hunting for faint statistical biases that could point to hidden channels. And quantum computing labs are joining the chase because quantum simulations run on qubits, not classical bits. A qubit can be 0 and 1 at once through superposition, letting the system explore many possibilities in parallel. But qubits are fragile. Heat, vibration, stray fields, and even cosmic rays can cause decoherence. Where quantum behavior collapses into ordinary behavior, that's why CRNs run mattered. The team held coherence long enough to push into extreme regimes and watch order emerge. Whether the lattice is real or not, the lesson is the same. The universe often rewards curiosity with surprises, and the surprises are where new physics begins. If the lattice turns out to be a feature of spacetime, then we are not living in a simple universe. We are living in a stacked reality where the visible world may ride on hidden architecture that can store and move information. Asterisk. If the lattice vanishes under replication, that is still a win because it shows where our models break and how to build better ones. Either way, the map expanded together. Thank you so much for watching all the way to the end. If you enjoyed this deep dive, please smash that like button, share your thoughts in the comments below. Don't forget to subscribe and turn on notifications so you'll never miss a future update. We've got a lot more exciting tech stories coming your way. Until next time, stay curious, stay inspired, and we'll see you in the next video. Goodbye.